Armed with some knowledge about entropy and how entropy is related to stability, we're going to return to polytropes and consider whether a polytrope is stable or unstable. And at various times, I've asked you to consider, given this particular polytrope and using your intuition, try and guess whether this will be a stable or unstable situation. Now we're going to learn some reasoning to back up that intuition. So the entropy gradient, this is the grad S over Cp. For an ideal gas, this is 1 over gamma grad log of the temperature minus the quantity gamma minus 1 over gamma grad log the density. Now, for a polytrope, the simplifying feature is to tie the density to the temperature, which takes us from two thermodynamic variables where we currently can't say anything to a single thermodynamic variable. So for a polytrope, the density is power law dependence on the pressure to some polytropic index m. And if we plug this in, in sort of full form, this means that rho over some reference rho is equal to t over some reference t naught, all to the m, and that keeps everything dimensionless so that things work properly and we can put things into logs with sort of trivial ease. So let's now write up our grad S over Cp for a polytrope. That is 1 over gamma grad log T minus gamma minus 1 over gamma. And we would have so we've got our grad log rho here, but rho, that's T to the M. So that's grad log T to the M. And since we have a log here, we can actually pull that m out in front of the logarithm. Oops. And m, where m is the adiabatic index. Okay, so let's clean this up a little bit. So grad S over Cp, this is equal to quantity 1 over gamma minus gamma minus 1 over gamma m, all times grad log t. Okay, so if grad log t, if we know anything about grad log t, then we can make some progress on understanding the potential entropy gradients that we're going to run into. Often the temperature decreases going outwards. Often grad log T is a quantity that's less than 0. This is especially true for isolated systems that aren't being externally heated. So we have a stratosphere where this is not true on Earth because it's being heated from the outside by the sun's UV. It gets complicated because in the sun, in the outer atmosphere, you also have a rise in temperature. That's due to effectively a cooling catastrophe in the corona, and it's kind of being externally heated by the sun itself, by other fluxes of energy coming up into the chromosphere and corona. But generally, things are hot deep in, they're cold outside because space is cold, and so the temperature gradient decreases. What that means is that whether S is a positive or negative quantity, it really depends on this. And in fact, usually grad T in a polytrope is a constant, and we often define it to be -1, non-dimensional -1, which means that grad log T is something like -1 over T in non-dimensional form. So it falls as you go out. So grad s, you might say, well, then it's obvious that grad s is going to be negative. But we have this prefactor here, and we need to determine how big m is. How big's m to have any idea of how big this internal prefactor is. And as I'm going to show you, it can actually switch sign. So let's consider the special case. So the special case is that that this thing is equal to 0. So is there a special case where, is there a solution to 1 over gamma minus a quantity gamma minus 1 over gamma times m equals 0? And if that special case exists, and it doesn't require absurd or extremal values of m, then we could see that there'd be both a positive entropy gradient regime and a negative unstable entropy gradient regime. Well, this is a straightforward system to solve since gamma is a constant, so we can cancel these gammas out, and this becomes m times gamma minus 1 is equal to 1 by moving the sign across, and that means that m is equal to 1 over gamma minus 1. And remember, this is the m that makes that whole prefactor equal to 0, and that means that grad s is equal to 0, whatever grad log t is. Doesn't matter. It could be positive, it could be negative. Grad s will still be 0. And because of that, we call this the adiabatic polytropic index, and you'll sometimes see it denoted m adiabatic, AD. Oops, accidentally wrote a B here. So m adiabatic, m AD. And we've met this before. As a reminder, recall that we know gamma for different ideal gases. So if gamma takes various values, m adiabatic will take other values. So if gamma is 5/3 for a monatomic ideal gas, then m adiabatic, that's 5/3 minus 1, that's 2/3 in the denominator, and once we flip it upside down, that's 3/2, which is equal to 1.5, or 1.5. That's m adiabatic of 1.5. If this is for a monatomic ideal gas. Monatomic. If we have a diatomic ideal gas, then we have a gamma of 7/5. And again, we do 7/5 minus 1, that's 2/5, 1 over, that's 5/2, which is equal to 2.5. And then we have a radiation dominated gas. We know that gamma, that's 4/3 for radiation. And 4/3 minus 1, well, that's 3. So here are a few different polytropic indices for adiabatically stratified systems. And remember, what that means is that if rho goes like t to the m, and m is m adiabatic, then the entropy gradient in the system is equal to 0. And you have an adiabatically stratified system. Okay, so what about if m is not equal to m adiabatic? So let's look at our prefactor. Let's look back at our grad s over Cp. This is 1 over gamma minus 1 over gamma times m, okay, times grad log t. Well, we can pull 1 over gamma out in front of this thing, and then this looks an awful lot like 1 minus m over m adiabatic times grad log t, or we can turn this into grad s over Cp is equal to 1 over gamma times m adiabatic times m adiabatic minus m times grad log t. And if we combine gammas and clean things up a little bit again, this might look like grad s over cp is now 1 over gamma minus 1 all times m adiabatic minus m grad log t. So the sign of grad s. The sign of grad s is going to be defined by the relationship between m and m adiabatic. I need to look up here for a moment because I believe I've made a sign error. So let's go back and check what we have for our equations earlier. All right. So as we come back down to our equation system here, yes, okay. So but we have to remember what's the my worry about a sign error was intuiting the next step, but we have to remember what's the sign of this. What's the sign of grad log t? So let's take the common condition of grad log t is less than 0. So this is like the troposphere of the Earth and the solar convection zone. So if grad log t is less than 0, then we can just look at the term m adiabatic minus m and ask what its sign is to determine the sign of grad s. So if m is greater than m adiabatic, then that's a minus signed term, and then it hits the minus sign of grad log t, and the entropy gradient is a greater than 0 quantity. If, however, when the temperature gradient is negative, if m is less than m adiabatic, then grad s is less than 0, and it's unstable. This is stable. And of course, m equals m adiabatic is the condition for stability. Grad s is equal to 0. So if we know the makeup of the gas, then we know m adiabatic. If we can measure m, the polytropic index, from a profile, then we can intuit whether a system will be stable or unstable to convective motions. I'm gonna leave you with one other thing, which is through experiments we found something further about the adiabatic index or the polytropic index m. In numerical experiments, and you can figure this out from sort of a simple math perspective as well. We found that when m is less than m adiabatic, so this is the convecting condition, grad s is less than 0, then the Mach number, which is the speed of the flows divided by the speed of sound, this is proportional to the difference between m adiabatic and m, and that's fundamentally because the Mach number scales with gradients of entropy, and so when the gradients of entropy are really big, then the Mach number is also big, and when gradients of entropy are very small, then the Mach number is small. So if m adiabatic minus m is an order 1 quantity, then typically your Mach number is also an order 1 quantity. And that means that you have flows that are highly sonic. So sound-like flows, or even supersonic flows. Faster than sound. But on the other hand, if m adiabatic minus m is a small quantity, if it's much less than 1, if it's an order epsilon quantity, then the Mach number is also much less than 1. And I believe the scaling is that the Mach number squared goes as epsilon. So Mach number squared goes as the same order epsilon above. But we'll learn the background of that in the future and gain more intuition and understanding for the sizes of nonlinear instabilities that we expect to see as we consider our non-dimensional fluid equations.